discussing algebraic numbers, and we want to prove the following theorem. If alpha and beta are algebraic numbers, then so are alpha plus beta and alpha beta. That is, sum or product of algebraic numbers is algebraic. Alpha plus beta is algebraic, alpha beta is algebraic. If alpha and beta are algebraic integers, then alpha plus beta is an algebraic integer and alpha beta is also an algebraic integer. And to prove this, we will use a sufficient condition for algebraic a number alpha in C to be an algebraic number. So we have seen that if you are able to find theta 1, theta 2, theta n as some complex numbers, and theta is a complex number such that theta times theta 1 is a combination of theta 1, theta 2, theta n with rational coefficients, and similarly theta, theta 2, theta, theta 3 up to theta times theta n, they are all combinations of theta 1, theta 2, theta n with rational coefficients. Then theta is an algebraic number. Moreover, if the coefficients in these linear combinations are integers, then theta will be algebraic integer. That is what we shall be using. And now we are starting with alpha and beta as algebraic numbers. So they will satisfy some monic polynomials with rational coefficients. So suppose fx gx belonging to qx are given by fx equal to xs to m plus a1 xs to m minus 1 plus etc. plus am, and gx equal to xs to n plus b1 xs to n minus 1 plus and so on plus bn. Here ai, bj, they are in Q, are such that f of alpha equal to g of beta equal to 0. So alpha satisfies a polynomial of degree m and beta satisfies a polynomial of degree n. They need not be irreducible. There are some polynomials satisfied by alpha and beta. Then we will show existence of a polynomial of degree m into n, which is satisfied by alpha plus beta, and similar polynomial satisfied by alpha beta. So we consider these powers of alpha. See that f of alpha is 0, so alpha raised to m can be written as a combination of powers of alpha up to m minus 1, alpha raised to m minus 1, alpha raised to m minus 2 up to alpha raised to 1 and some rational number. So alpha raised to m is a combination of powers of alpha of smaller degree. Similarly, beta raised to n, from this equation that g beta is 0, so beta raised to n will be minus b1 beta raised to n minus 1 minus b2 beta raised to n minus 2 and so on minus bn. That is what we shall be using. So consider the even numbers 1 alpha alpha square up to alpha raised to m minus 1. These are m numbers. Multiply these by beta. So beta, alpha square beta, etc. alpha raised to m minus 1 beta. Then multiply by beta again. So beta square, alpha beta square and so on. Alpha beta square, alpha square beta square and so on. Alpha raised to m minus 1 beta square. Finally, you consider beta raised to n minus 1 degree of, so beta satisfies the polynomial of degree n. So that n I consider. So beta raised to n minus 1 comma alpha beta raised to n minus 1, alpha square beta raised to n minus 1 and so on. Alpha raised to m minus 1 beta raised to n minus 1. So these numbers we call as theta 1, theta 2, theta capital N. So let n equal to mn. Consider the above mn numbers in C. They are all complex numbers as theta 1, theta 2, etc. theta capital N. Capital N is small m into small n. So here these are theta 1, theta 2, theta 3 and so on. Lastly you get theta capital N. Now we will multiply these theta 1, theta 2, theta capital N by alpha plus beta and see what we get. So any element in this list is of the form alpha raised to some I into beta raised to some j, and multiply this by alpha and see what happens. So alpha times alpha raised to I beta raised to j, it can be considered as alpha raised to I plus 1 into beta raised to j, and if you take I zero less than equal to I less than m minus 1, then I plus 1 is less than equal to m minus 1. Then so if this is some theta I or theta t, we can say, for one less than 0 less than equal to j less than equal to n minus 1, this is some theta j, and alpha times theta j is again some theta. So alpha times theta t is again some theta t dash, some theta t dash. For equal to m minus 1 alpha times alpha raised to m minus 1 beta raised to j is equal to alpha raised to m beta raised to j. And alpha raised to m you can write as a combination of previous powers of alpha. So it is minus a1 alpha raised to m minus 1 minus a2 alpha raised to m minus 2 minus and so on minus am times beta raised to j. Equal to a q combination of theta 1, theta 2, theta n, because these alpha raised to m minus 1, beta raised to j, they are some theta, their combination. So you see that for 0 less than or equal to j less than or equal to n minus 1, you make two cases, I is such that 0 less than or equal to I less than m minus 1 or I equal to m minus 1. In any case, what happens is when you multiply this number by alpha, you get a combination of theta 1, theta 2, theta n. So write alpha times theta t equal to summation h you can say ti theta I equal to 1 to n. H ti belong to q. If alpha is an algebraic integer, we have that alpha satisfies a monic polynomial with integer coefficients which we can take as f. So ai are in z, we have ai in z, so hti belong to z, hti belong to z. In a similar manner, we can consider beta times alpha raised to I, beta raised to z. Similarly, we can show that beta times theta t is equal to summation, let us say k ti theta I equal to 1 to capital N. Capital N is small m into small n with k ti belonging to q. If beta is an algebraic integer, we can take bi belonging to z, and the proof tells us that So k ti also belong to Z. Therefore, alpha plus beta times theta t for any t between 0 and capital N, alpha plus beta t you can write as summation h t I plus k t I times theta I equal to 1 to capital N. And this is a combination of theta 1, theta 2, theta n with rational coefficients. This is combination of theta 1, theta 2, theta capital N with rational coefficients, and it holds for every t and holds for every t 1 less than equal to t less than equal to capital N. Therefore, we can say that alpha plus beta is an algebraic number. Okay? Therefore, alpha plus beta is an algebraic number. If alpha algebraic integers, then HTI plus KTI belongs to Z, 1 less than equal to t less than equal to n, and 1 less than equal to I less than equal to n. And therefore, alpha plus beta is an algebraic integer. Therefore, alpha plus beta is an algebraic integer. In a similar manner, we can get the result for alpha into beta. So look at this beta times theta t equal to beta times theta t equal to summation k t I theta I equal to 1 to n. This is for all t 1 less than equal to t less than equal to n. Multiply by alpha and see what happens. So alpha times beta times theta t equal to summation k t I equal to 0 to n alpha times theta I. But again, alpha times theta I you can write, this is t, so I equal to 0 to n theta I. Now I equal to 0 to n k t I alpha times theta I you can write as summation h I comma z theta z say equal to 1 to capital N. And that's a combination of theta 1, theta 2, theta n equal to a combination of theta 1, theta 2, theta capital N with rational coefficients therefore alpha beta is an algebraic number. If alpha beta are algebraic integers, as before, KTI and HIZ are integers, and so alpha beta theta t is a combination of theta 1, theta 2, theta capital N with integer coefficients. And this holds for 1 less than equal to t less than equal to capital N. And that means alpha beta is an algebraic integer. Therefore, alpha beta is an algebraic integer. And this can be said in different words. Corollary. The set of all algebraic numbers forms a field. And if you take algebraic integers, the set of all algebraic integers forms a ring. It's a commutative ring with unity. Commutative ring with unity. And the proof is what we have done just now, that if you take two algebraic integers, then their sum and product is an algebraic integer. An algebraic number, what happens? Alpha is algebraic number, beta is algebraic number. Then their sum is an algebraic number. Their product is an algebraic number. Minus of alpha is algebraic number. If alpha not equal to 0, 1 upon alpha is an algebraic number. So all this shows that the set of all algebraic numbers is a subfield of the field of complex numbers. So proof of the corollary. If alpha beta are algebraic numbers, then so are alpha plus beta minus alpha, alpha beta, and 1 upon alpha in the case when alpha not equal to 0. and therefore the set of all algebraic numbers forms a subfield of the field of complex numbers. That means it is itself a field. Therefore, it is a field. This is the criterion for a subfield, that you have a non-zero subset which satisfies this property, that it is closed with respect to addition, then negative, product and reciprocal. Then it's a subfield. You don't have to check other properties like distributive property and so on, because they are already there in the superset. Like complex numbers is the superset. It has all the other properties, commutative property, associative property, distributive property and so on. Once you check these properties that close with respect to addition, minus, so or difference we can say, product and reciprocal. Similarly for the algebraic numbers, integers, if alpha, beta are algebraic integers, so are alpha plus beta minus alpha, alpha beta. Therefore, the set of all algebraic integers forms a subring of C. That is, it is a ring. So algebraic integers forms a ring. We have seen that there are plenty of algebraic numbers, but still the complex numbers which are not algebraic numbers, these are called transcendental numbers, and they are huge in number, in the sense that algebraic numbers are countable, whereas the transcendental numbers are uncountable. And some examples are there, like we can prove E, pi, they are transcendental numbers, but the proofs are complicated. We shall now talk about transcendental number, specifically the Liouville number or Liouville constant. So in the 1851, Liouville gave this example of the following transcendental number. This number is alpha equal to summation 10 raised to minus j factorial j equal to 1 to infinity. So this is 1 upon 10 plus 1 upon 10 square plus 1 upon 10 raised to 6 plus 1 upon 10 raised to 24 plus 1 upon 10 raised to 120 and so on. Or in decimal notation we can write it as 0.11000100 and then there is 1 at the 24th place, again zeros and so on. So you see that ones are very sparsely situated on the right hand side of the decimal point, and at other places you have zeros, and that is why this is the reason that this alpha is a transcendental number, and the proof of this goes like this. Usually proof for a number to be transcendental is complicated. Here mean value theorem is used to show that alpha is transcendental. So this is what you want to prove. So to prove that this is transcendental. So suppose alpha satisfies some polynomial with integer coefficients. Suppose alpha satisfies fx equal to 0 where fx belongs to zx and this is a non-zero polynomial. So suppose fx equal to summation Cj x raised to j equal to 0 to n. Suppose this is of degree n, that is Cn is not equal to 0. Here all the Ci they are in z, that is they are integers. Now look at the derivative of this polynomial. So f dash x is equal to summation j times Cj x raised to j minus 1 j equal to 1 to n. Now if x is between 0 and 1, then mod of f dash x is less than equal to summation j equal to 1 to n j times mod of Cj, and see that mod x less than 1 or x is between 0 and 1, so that goes and we can just have summation j times mod of Cj, and suppose this is some constant C, capital C. Now consider the mean value theorem, and you take the nth partial sum of the series for alpha, and alpha k equal to summation 10 raised to minus j factorial j equal to 1 to k. This is the kth partial sum for the series for alpha. And we will consider f alpha minus f of alpha k. See that this epsilon k is the error alpha minus alpha k. If you stop at alpha k, then this is the error. And what is mod of alpha minus alpha k? This is actually summation j equal to k plus 1 to infinity 10 raised to minus j factorial. Now we can say, we can get a bound for this less than. So it starts with 1 upon 10 raised to k plus 1 factorial into bracket, so we take it outside, and 1. Now the next term is 1 upon 10 raised to k plus 2 factorial. So if you take out this 1 upon k plus 1 factorial, you will see that what is left out is certainly less than 1/2. Similarly, if you take the next term, it is less than 1 upon 2 square and so on. And this is equal to 2. So this is 2 upon 10 raised to k plus 1 factorial. So if you stop at the kth term in the series, then the error is less than 2 upon 10 raised to k plus 1 factorial. Okay, now you consider f of alpha minus f of alpha k mod of this. By mean value theorem, this is mod of alpha minus alpha k into f dash theta mod of this. For some theta between alpha and alpha k. Here we have a bound for this and a bound for this. So mod of alpha minus alpha k is less than 2 upon 10 raised to k plus 1 factorial, and alpha and alpha k, they are both less than 1. Theta is between 0 and 1. Therefore, we can use the bound for mod of f dash x for x between 0 and 1. So here 0 less than theta less than 1. So mod of f dash theta is less than equal to c, that constant that we considered. And mod of alpha minus alpha k is already less than 2 upon 10 raised to k plus 1 factorial. And therefore, mod of f alpha minus f of alpha k is less than 2c upon 10 raised to k plus 1 factorial. So this is 1. Now you look at the left hand side, mod of f alpha minus f of alpha k. Alpha satisfies f of alpha equal to 0. Alpha is a root of the equation fx equal to 0. So this is 0 and therefore this thing is just mod of f of alpha k. So now our polynomial fx is summation Cj x raised to j equal to 0 to n. So f of alpha k, when you substitute, it will be summation Cj alpha k raised to j. Now look at alpha k. So alpha k is summation 10 raised to minus j factorial j equal to 1 to k. So you see that here this is 1 upon 10 raised to j factorial. So if you write it in the form numerator upon denominator, then in the denominator you will get 10 raised to k factorial. So alpha k, and in the lowest term that cannot be cancelled with anything. So f of alpha k has 10 raised to k factorial in the denominator in the lowest terms, or just alpha k. Let me say here alpha k has 10 raised to k factorial in the denominator in the lowest form. If you look at f of alpha k, then it is summation Cj x raised to j. So if you take j equal to n, that term, that will have 10 raised to n times k factorial in the denominator. Therefore, f of alpha k has 10 raised to n times k factorial in the denominator. Now, f of alpha k, is it 0 or not? That is the question. But these partial sums alpha 1, alpha 2, etc. are distinct. The partial sums alpha 1, alpha 2, etc. they are distinct. Our polynomial fx can have at most n zeros. So fx has at most n zeros because n is the degree of fx. after some stage f of alpha k is not equal to 0. Hence, for sufficiently large k, f of alpha k is not equal to 0. And now f of alpha k is numerator upon denominator. So, mod of f of alpha k is equal to numerator upon denominator. So, this denominator is 10 raised to n times k factorial. It may be that something cancels. In any case, even if there is some cancellation, we can say that this is bigger equal 1 upon 10 raised to n times k factorial. Now, mod of f alpha minus f alpha k, that is mod of f alpha k, is bigger equal 1 upon 10 raised to n times k factorial. Whereas mod of f alpha minus f of alpha k by the mean value theorem was less than or equal to 2c upon 10 raised to k plus 1 factorial. Therefore, this quantity is less than or equal to 2c upon 10 raised to k plus 1 factorial. Therefore, 1 upon 10 raised to n times k factorial less than or equal to mod of f alpha minus f of alpha k less than 2c upon 10 raised to k plus 1 factorial, and this holds, that is 1 upon 10 raised to n times k factorial less than 2c upon 10 raised to k plus 1 factorial for sufficiently large k. Sufficiently large k means all k after a certain stage. Now, this is a contradiction. That is because, see that this is k plus 1 factorial. So, and this 2c is a constant. So, we have 10 raised to k factorial times k plus 1. So, because this is just n times k factorial and k can become very large and this is a constant. So, this is not possible for sufficiently large k. This is a contradiction. For large k, since n and c are fixed, and that contradiction tells us that alpha, that is the Liouville number or Liouville constant, cannot satisfy a polynomial with integer coefficients. Thus, alpha equal to summation 10 raised to minus j factorial, j equal to 1 to infinity, cannot satisfy a polynomial, a non-zero polynomial with integer coefficients. That is, alpha is a transcendental number. So this was the first example of a transcendental number, and later on E was proved to be transcendental, pi was proved to be transcendental, and this was done somewhat later. The proofs for the transcendental nature of E and pi, they are more complicated than this. It was proved by Cantor. This was in 1874, that there are infinitely many or uncountably many transcendental numbers. Then there was a theorem, later on Hilbert asked the following question, that if A is not equal to 0 or 1 is algebraic. It is an algebraic number, and B is algebraic irrational, then is A raised to B transcendental. So Gelfand and Schneider, they proved that answer to this question is yes. So it is Gelfand-Schneider theorem, and because of this we have many examples of transcendental numbers. So 2 raised to root 2. Here A is equal to 2 and B is equal to root 2. So A is not equal to 0 or 1, it is an algebraic number, and root 2 is an algebraic number which is irrational. Then 2 raised to root 2 is, this is transcendental. If you take minus 1 raised to minus I, this is e raised to pi I raised to minus I, and that is e raised to pi into minus I square, that is plus 1, so it is e raised to pi. This is called Gelfand's constant, and this is transcendental. Here minus 1 is not equal to 0 or 1 is an algebraic number, and minus I is not a rational number. So it is an algebraic number, it is not a rational number. Therefore minus 1 raised to I minus I must be transcendental, and that is why e raised to phi is transcendental. So plenty of proofs, plenty of examples you can get of transcendental numbers by using the theorem of Gelfand and Snyder.